if we think about what kind of things we need to deal when we try to improve reliability of the system. So basically, this is still the same stuff what we have been discussing. So we start thinking at what are the actual failure mechanisms which can cause the system to fail. And of course, this now can be in different levels. So we can consider it in component level, board level, system level, product level, whatever level. And then how can we estimate the probability of these failure modes and mechanisms without without needing to wait some time which is not practical. So of course we can always monitor the field behavior. So when we start manufacturing something, we start selling something, then the customers start using it, then we can start collecting the data, how these systems behave in the normal field operating conditions. But of course, then we might get and see the problems after several years, which means that already we may have kind of done something which is not practical. I mean that there could be some design mistakes which are really costly. So therefore we need to utilize somehow testing and accelerated testing. And this is basically the main idea what we concentrate on the next part of the course. So starting after the first intermediate exam. So how can we, with a clever way, have the probability of the failures estimated? And then on the other hand, if we know the probability of failure for each failure mode in every component, so basically we understand what can happen, then and we also know how our system is working, so how these components are assembled, then can we somehow calculate or estimate what is the probability of the system to fail. So this is something that today we I will propose the simple approach how you can calculate the system level reliability if you know the component level reliability. So maybe that's the most important point for today. And then of course, if we think that there could be some challenges related to our design, then how can we react and increase the reliability of the whole system? So here there could be different type of approaches, but quite often it is the kind of the idea of weakest link. So if we improve the reliability of the weakest link, then we improve the reliability of the system. On the other hand, as we will see, the system reliability is always dependent on the complexity of the system. So if we are able to decrease the amount of parts in the system, that also increases the reliability of the system. So kind of to conclude, the design for reliability, what is our aim is to understand, identify, and prevent the failures before the devices are even built. Why is that? There are some numbers. So this is kind of you have this in the other form of slides in my previous lecture slides. So I just merged two slides together. So 70 to 80% of all defects can be related to design. So for one way or the other, the decisions what you do in the design table also affect on most of the failures. They might not be direct design mistakes, but still the design significantly affects on those failures. And also design affects on the manufacturing and manufacturing costs. Because, for example, as we discussed already previously, by needing certain functionalities, you need certain components and component types. And if you have certain component types, then basically you need to have certain assembly methods. And assembly methods then define also the manufacturing cost, at least partly. So let's say that more, if you need to have higher integration components, let's say you need to have integrated together some, let's say, MEMS components, logic and memory. That typically means that you have more IOs, so you need more interconnections to that component. And if there are size limitations, thickness limitations, like, for example, handheld mobile devices, then it directly means that you need to decrease the amount of interconnections, decrease the size of the interconnection. So you need smaller micro bumps or smaller solder interconnections or whatever. And that directly defines what kind of mounting machines you need to use, what kind of inspection tools you can use, and so on and so on. So that's the reason that surprisingly large fraction of the reliability as well as manufacturing costs are defined in the design table. And that's the reason that this design for reliability approach is to try to think the reliability up front. So again, this pessimistic view that trying to figure out what could go wrong in design, material selection, processes, wherever, and then sorry, make clever decisions in order to decrease the probability of these failures. And after that, then we need to somehow verify that our design processes have been correct, and that is done with the accelerated tests. And again, we need to remember that we are talking about different types of failure mechanisms. So we are talking about these overstress mechanisms, like you remember in our strength approach, we have this threshold stress failure, meaning that something is that the stress is higher than the strength, and then we end up a failure. And then we have these wear-out mechanisms where this kind of cumulative effect of stresses is having the effect of causing the actual failure. And there are, in the literature, you can find different types of tables on this. This is maybe the most typical one. This is, if I recall correctly, this was from Tummala's book. So we have the overstress failures here, and typically the overstress failures are divided into mechanical or thermomechanical and electrical failures, and then we have the wear-out mechanisms, and there, in addition to these mechanical and thermomechanical and electrical, there is chemical stresses. Quite rarely, the chemical stresses are something that which kind of would belong to this part. There might be something related to process residues or something like that, but they are very rare cases. So this is the typical definition. If we look a little bit at wider perspective of applications, for example, where radiation could be included, then this is again a slide which I stole from Kause, University of Maryland. So here, basically the same idea, but they have added this radiation here. So for example, charge trapping and this kind of a thing which could also cause failures during the useful life. Also here, the chemical part is empty for the overstress mechanisms. So now, when we understand that we have different types of mechanisms, then based on those, we can start thinking about our, let's say, verification process. How do we verify that our product will be reliable enough? And now you remember that our reliability definition, there was two critical things related to this one, is the acceptable failure level and under certain conditions. So it means that now we need to define that what is the acceptable failure level, and that was mainly related to this one. So how many random failures or overstress failures we can allow, and on the other hand, we have this under certain conditions, meaning that what kind of stresses the product will see, and because those stresses then cause the decrease in strength, which then later on or during the lifetime start causing these wear out mechanisms. So this process is something which we now start to approach, and this stage gate process, it's just a simple way of thinking that in here we have the target reliability. So how do we ensure that we meet the target reliability is these kind of steps or stages. So first we have the idea stage, which is basically understanding what do we need, what is our target. So basically after this one we should know where we are, and maybe have some kind of a first idea that how close or how far we are on the target. Then we have the evaluation phase, which is called design assessment reliability testing, DART. That means that we try to figure out a fast and simple way to see that we don't have any significant design mistakes. And this is typically done with the highly accelerated test. Then we have so-called design maturity testing, and this is the part which typically takes the most amount of time, because here we are using these accelerated lifetime tests. So here the test might take months to execute. And then after that, we basically think that, okay, now reliability is high enough, so we can start doing the proto manufacturing and start producing the mass manufacturing. And then after that, we just monitor that our manufacturing produces high quality enough, the yield is high enough. So another way of putting this is that now here in y-axis we have the reliability, whatever it is. In this diagram, it's now puts this mean time between failures, but we can maybe consider that this is just generic reliability. And then we have these different stages here, stage gate 1, 2, 3, and 4. And now we start with this stage gate number 1, which is understanding the requirements. So how do we understand that what is needed? So what is this target level, and then where we are with the start point. So this is all these things are done on the design table. So before we need to manufacture anything, so we don't need to have even breadboards or prototypes at this stage. So then we start with the testing after this point. But first we need to know that where we start with, what is the kind of first guess how reliable our product could be. And now this reliability calculations or reliability metrology means that we have some kind of tools to measure or model the reliability. And quite often the tools are this kind of a mathematical tools of probability and statistical distributions. So as I said, sometimes I'm not that fond of these, because sometimes they might kind of hide the actual failure mechanism. You don't really, just playing with the numbers, you don't really find out the proper reason for the let's say unreliability. And then of course you don't have any tools to improve it. But this does not mean that these wouldn't be important. Yes, they are extremely important, because you need to have tools to analyze your data. You cannot, if you have millions of units in the field and you get some data, or you have hundreds or thousands of samples in your test and you get some data, you need to have some tools in order to analyze the data, see the differences between different, let's say, components, materials, or use conditions or whatever. So you need these tools in order to collect, classify, and process the data. So it helps in understanding the failures and identifying the potential failure sources. But you need to support this one with the failure physical analysis. So basically understanding the individual mechanisms behind in order to really make the improvements. So now very quickly, few slides on this, what kind of definitions and functions are typically used in this kind of a reliability metrology. And basically, everything is kind of starting from so-called cumulative failure function. Cumulative failure function is just a fraction of devices which have failed after a certain amount of time. And then the other function related to that one is the reliability function. So this then means how many are still living after a certain amount of time. So you have this simple equation. So this is just a cumulative number. And then we have so-called failure density function. And that describes that how many failures the system or device experiences during a certain time interval. And of course, this is the time derivative. So from the failure function, cumulative failure function is the failure density function. So this is just a definition. And then previously I said that there is no experimental evidence that the bathtub curve would exist in real life. So now here, let's see, I need to take off the pointer. Let's see if my hyperlink works. So this data, which I'm now presenting, is taken directly from Rao Tummala's book, Microsystem Packaging Handbook. So it is a failure data from 1,000 components, flip chip components. Really does not matter what flip chip here means. We will go on to that in the last part of the course, but basically it's just a bare silicon die, which has typically solder pumps with it directly attached to a substrate. And in the thermal aging, so just put them these 1,000 components in high temperature, then they have measured the failure rates. Let's see if this works. So hopefully you now see these thermal aging results. So in the left column, you see the number of hours. So this is the first 10 hours, the second 10 hours, so after 20 hours, 30 hours, and so on. And the total test time was 400 hours. And here in the second column, you see that how many devices failed during this 10-hour period. So out of those 1,000 samples, then during the first 10 hours, 103 samples failed. And then during the second 10 hours, it was 72. During the third 10 hours, it was 52, and so on. And then you end up having the cumulative failure function. So of course, 100 out of 1,000 is 10%. And then you have 175, which is 17.5%, so 18%, and so on. So now this describes how the amount of failed units is developing as a function of testing time. And then here you can get the failure density function. So how many, what is the fraction of failures with respect to the time period? So always you have 10 hours. So it means that when you have more failures, then of course the failure density function is highest. And now if you draw these diagrams, you see that the cumulative failure function is shaped like this. And then if you take the time derivative, you get very nice symmetrical shaped bathtub curve. So we have these early failures. So meaning that these first failures here are related to quality related issues. So for example, there could be voids or poor wetting in some of the samples. So that is the reason that the failure rate in the early stage is high. Then we have this random failures or constant failure rate. So in the middle of the testing, then you have almost equal amount of failures in every 10 hours. And then in the end, you start seeing that now the wear out starts, so the failure rate starts to increase, and you end up in the end of life. Okay, sorry, here. And now, of course, the question is that, okay, I already said that this is not proven never. And then if you go back to the data and start looking at, I would say that I wouldn't trust this data. It is too symmetrical. So maybe this is not the real data, just yeah. So I fully agree with you, Scott, so that this must be Excel data. So it's too symmetrical. So if you look at these numbers, 103, 103, 72, 72. So it is definitely made with Excel, not with real test. Maybe the purpose was just to show that this is how it should look like, but in real life you wouldn't, of course, get this nice symmetrical shape. Maybe something similar or something which could look like this, but this is definitely not correct data. Okay, but that was just to kind of show that what these functions mean. What is the cumulative failure function? Like this. Of course, the reliability function is then the opposite way, and then we have the failure density function. So now we've come back. Hopefully you see now the original slide. So how does failure density function calculate? So basically failure density function is here. So basically you can get it from, you check that what is the cumulative failure function, and then divide it by, in the previous case, by 10 hours. So how many failures were there in that specific time period, and divide it by 10 hours, and then you get the failure density function. So here is the kind of the problem with this way is that it does not tell you any information what is the failure rate of those units which are still under use, so which have not failed, because of course that would be important if we are able to, with the testing, to get rid of the infant mortality. Then we are mainly interested on those samples who are still operational, and then that's the reason that one is more commonly using so-called hazard rate or failure rate, which is so-called instantaneous failure rate. So it's just the failure density function, this FT, divided by the reliability function. So we are comparing the failure density function to those units which are still living. And if we assume exponential distribution, then basically the hazard rate is equal to the failure rate, and it's the inverse of mean time to failure. So this is just pure kind of definitions and mathematics. So then how do we in practice treat the data so that we get some numbers out which helps us making let's say conclusions, because the more numbers you have, the more difficult it is to really see that, okay, what is the, for example, correlation? You have a data from the field, you have the data from your test. So what is then the way to tell that, okay, now the test which we have utilized is relevant, and it's most probably let's say causing similar types of failures that what we see in the field. So we can utilize the data in order to predict the reliability in the field data. So we need these kind of tools and use different type of statistical distributions on that. And when we are talking about reliability statistics, then there's one distribution which is way more frequently used than any other, and that's so-called Weibull distribution. I'm sure that you have seen this Weibull distribution beforehand. So maybe, as I said, the point here is to being able to compare and analyze the failure patterns. So how the failures are distributing over time. And with the Weibull distribution, you basically can kind of get or squeeze your test data into two numbers, which give you two different things. And the first one is the ETA parameter, which is here. So that's the so-called characteristic life. And basically that is just the average life. This is purely coming from the mathematics, that this characteristic life gives the fraction of the time where 63.2% of the devices have failed. So little bit more than half of the devices. So it's not directly average lifetime, but basically quite close to that. So this gives you the average life. And then we have maybe the more important parameter is this beta parameter, which is called shape factor. And that shape factor measures how the failure density is distributed around the average lifetime. So it is kind of a measure of the shape of the distribution of the failures. And what that actually means is that it's an indication of the actual failure mechanism. So basically we can have first a simple interpretation. This is a slide which I already showed you beforehand. So if the beta parameter is smaller than 1, then we are talking about this decreasing failure rate. So early failures, Monday morning products. If it's close to 1, then we have random failures. And if it's greater than 1, then we are here in the wear out. So basically this beta is the slope of the curve. So as the statics is mainly used in this area, the wear out phase, then more important for us is the not if the beta is smaller or larger than 1, but what is the actual value. Because if we have data, different data sets, and then the beta values are close to each other, so basically the slopes are almost identical, then there's a high probability that the failure mechanism is the same. If they are different, then there's a high probability that the mechanisms are different. Is the beta time dependent, or we use different constant on betas? So basically, in that sense, beta is time dependent than that we have different beta values in the different type of lifetime. But when we do, let's say, reliability testing, we might, for example, get a data set where there are two clearly different distributions or different parts. So we have, let's say, data where one part of the data belongs to certain failure mechanism, and then another part of data belongs to another failure mechanism. And for example, this first data could be either different beta, which is greater or smaller than 1, or it could be even so that the beta is indicating that now these are quality defects and the other ones are defects which are caused by wear out phenomena. So we can have kind of different beta values as a function of time, but it's not that beta would be kind of changing as a function of time, because beta is describing a different mechanism. So in that sense, it's not you cannot formulate a function on beta where time would be a variable. Hopefully I made myself clear. Okay, good, thanks. Okay, so as I said, I don't want to go into deeper in this kind of statistical mathematics. If you need them, there's huge amount of good books, and for example, this Patrick O'Connor's book, which I have shown quite many times, that's quite nice. It contains all the basic things, and then of course Milton Arnold is one of the great books on statistical mathematics, which could be used here in the reliability analysis. I would say that it would be if you are working with reliability, then anyway, you will face Weibull's distribution very, very frequently, but there are, of course, some other distributions also. So this is just an example. I'm definitely not going to ask any of these kind of things that where if you have certain failure mechanism, what kind of distribution you would use. This is just to show that, okay, there are different type of application, different type of failure mechanisms, and then people are using different types of distributions in order to analyze those. So for example, some of the failures are these kind of more overstress failures, shock failures. Sorry about the spelling mistake there. And there you use different distribution. But for wear out phase, then typically the Weibull is the distribution to use. And I also added in your slide this kind of a table where these different functions are defined, just to have some kind of a reference there. If you want to check what this failure density function really meant or whatever. So the only thing which I didn't yet state was this availability. So the availability is just what is the fraction of time when the system is operational with respect to the whole operational time, so uptime and downtime. So this is related to the systems which can be repaired. So the difference between mean time to failure and mean time between failures is just that the mean time to failure is for unrepairable systems and mean time between failures is for repairable systems. So basically you can increase the operational time by doing some kind of a maintenance work on those. Okay, but that's enough for that one. And then maybe the most important thing, which is again more that you get to know the basic idea behind how you can do these reliability predictions or calculations. This is not that I would say that this gives some absolute truths, definitely not. But it's good to know, it's good to understand what is the basic idea behind all these different reliability prediction tools. And now also this is good to kind of make the clear difference between what are the failures which are random failures, so these overstress failures, and which are failures which are caused by wear out. And you have completely different tools for those. And this first example here tries to highlight what is the difference between this MTTF, mean time between failures, or mean time to failure, and then lifetime. And in fact, to say that there's no correlation. There's no direct correlation between those. So even this mean time to failure or mean time between failure somehow indicates that should give us some understanding on the lifetime, but it's not. It is giving you the reliability in normal operational life. So it is now giving the values which are related to in the bathtub curve in the second part, in the constant failure rate part. So failure rate, that is typically expressed that how many failures you have per million or billion operational hours. And on the other hand, mean time to failure or mean time between failures is typically expressed in terms of hours. So on average, in how many hours the system is failing once. So basically, if you have MTBF of 1,000 hours, it means that you have one failure of the system per 1,000 hours, or vice versa. If you want to use this definition, then you have 1,000 failures per 1 million operational hours. So again, this is just something which makes our life confusing because we have different definitions, but just keep in mind what is the difference between failure rate and MTTF or MTBF. So now, if we look back to our previous definition and consider that what this really means, what this MTTF really means is, and here is an example that if a system or product has an MTTF of 20 years. So what does it mean from lifetime point of view or failure-free time point of view? So the question is that if MTTF is 20 years, so what is the share of failed units after 5 years? And then we can use this previous equations from the previous slide. So failure rate is the inverse of MTTF, and we assume the exponential distribution. So we can calculate the share of failed units, and we end up in a value of 22%. So it means that more than every fifth of the sample products devices have failed after 5 years. Even the MTTF is 20 years. So that means that the point here is that MTTF is a statistical parameter, and it does not indicate lifetime, it does not indicate failure-free time. So that's why sometimes these MTTF requirements seems quite insane. But what they actually mean is that you need to just push the random failures down. So I, for example, remember one case, this relatively large Finnish telecommunication system. We were discussing that their customer wants that the system provider should verify that the MTTF for this whole telecommunication system would be 50 years. And what does that mean? That again does not mean that this telecommunication system should be operational for 50 years, because of course nobody wants to use today's telecommunication. It's completely out of date after 10 years. So in that sense, MTTF of 50 years sounds kind of strange. But on the other hand, it's not strange if you start thinking about that it does not have any meaning in the lifetime or operational time. It's just an indication of what is the amount of random failures. So that's the reason that you need this very high MTTF for the system, so that it's practically the reliability during the normal operational lifetime. So let's say next 5 or 10 years is small enough. So that is the point there. And then how do you verify that with testing? So that is the critical question, because now if you have a certain very long MTBF or MTTF, then if you want to push the value for high, so that you get very low amount of failures in the first 5 or 10 years, that means that you need to have huge number of samples, because this is again just statistical mathematics. So you need to make sure that the distribution is far on the right on the longer lifetime, so that the fraction during the kind of actual operational years is small enough. And you can do that one only by having large number of samples. And you can understand that when we are talking about, for example, telecommunication products like base stations, so you cannot test thousands of those because they are very expensive, and they would take huge amount of time, money, resources to test thousands of those. And then how do you do it? And that's the big question, because you should either need to use extremely long testing times in order to verify the reliability, or you need high number of samples, and both are unpractical. So that brings the big question that how one should do it, and for example, then being more clever with the testing conditions, so you can accelerate the test, you can use combined loading conditions and these kind of things, and then play with the mathematics, so you can kind of verify the customer that okay, these are reliable enough products, and this is how do we kind of verify it. So sorry for taking quite long time on this, but this is kind of very typical thing which confuses people when you think about mixing the lifetime expectations and then mean time to failure or mean time between failure requirements, because they are completely different. Of course, when you have more robust system, so this is high, then typically also your lifetime is high because you have more robust, but they don't have the direct link because they are kind of describe different things. Okay, so how do we then start calculating things? So which are the ways that we would get some kind of a number for this one? So if our customer needs to have the number, then you can utilize either testing or you can use this kind of a prediction models or mechanisms, not mechanism, maybe models is best to describe it. So you have a way to calculate the system level failure rate based on the component level. So this is what this MTTF or MTBF calculations refer to. And now if we compare, as I already said, we had this FMEA technique that was considered as a top-down. So we started from the system level or product level and then go downwards into the parts and thinking that how the parts would fail. And now this methodology for MTTF calculations is completely different, opposite. So this is called bottom-up technique. So we start from the components from which the system is made of, and we basically assume that we have a data for each component, and then if we assemble the system or product from these components which we know, then we can calculate the reliability of the system. And now we need to consider different types of systems. So we have systems in series, which means that the idea is that if one part fails, then the system fails. And then we have some systems like in medical or telecommunication, where we have redundancy. It means that we treat this system mathematically so that it would be parallel. So if one part fails, then there is a backup system which overtakes. So of course the system needs to have this hardware to have the parallel system, but also the system needs to be clever enough that it can itself notice that okay, now this part fails, so the other system, the redundant system must take over, and so then you can utilize the redundancy. So now the idea is that we calculate the system reliability based on the component level reliability, and we assume either we have series or parallel system, but the basic assumption is that each element in the system is independent, meaning that this component has a certain failure rate and this component has a certain failure rate, but the failure rate of this component does not affect on the next one. And this is maybe the biggest drawback of the whole idea behind this. And with this, what I would like to emphasize is for example, this system. So let's consider that here we have the system, and here we have just two components where the system is composed of. So we have an electronic component, whatever, BGA component, and then we have the motherboard of the system. And now we want to evaluate the reliability of this system based on the reliability of this component and based on the reliability of this board. Is that possible? Sometimes yes, if we are talking about certain type of failures, but sometimes definitely not. So let's think that we put this system under a cyclic thermal load. So let's say that this system sees temperatures from -20 up to 150 degrees centigrade. And then we think that if we get the reliability of this component under those conditions, and then the reliability of this board under those conditions, so can we estimate the reliability of the system on those conditions? And the answer is no. Because if we start cycling this one, the weakest link is definitely somewhere inside the component. So maybe the wire bonds which are connecting the actual component to the component substrate or whatever. If we are cycling this bare board, the weakest links are most probably these plated through holes. But if we assemble the components of the board and start cycling the system, then definitely under those conditions, the weakest links are these solder interconnections because of the CT mismatches and so on. We'll come back to this later on. But the point is just that if we try to evaluate the reliability of this system based on knowledge of reliability of this one and this one, it is valid only in certain stress conditions, but not for all stress conditions, because the failure mechanism, the weakest link, is completely different. If you put this component in cyclic thermal loading, then these solder balls here, they don't withstand any stresses because they are not attached to anything. Only the interface here might have some local stresses, but the actual solder interconnects nothing. But if you attach this to the board, then this is definitely the weakest link. So this is just to point out that we need to understand that this requirement that each element is independent, you need to understand that it's not valid always. This is also maybe more simple example is that you have two components side by side, and the other component produces quite a lot of power losses. So it means that the temperature of the adjacent component is also higher than the environmental temperature, use temperature, because of the power losses. So you cannot claim that these components would be independent because they are, the other component is affecting on the local temperature of the components outside. Okay, so basically the idea now why I'm talking about this is that we need to have this starting level of our reliability. So you remember now, look back to the stage gate process. So we need to have this starting level, and then we have our target level, and we need to know that where we are starting. So this is where these calculations are most powerful. So we know that, okay, how much we need to do in order to verify the reliability, and we can also compare different approaches. So for example, we can compare different designs. What is the effect if I change this component to the other one for the whole system reliability, or if I change the let's say layout or something else to other? So it has cost effects, but it can also have reliability effects, and what is the kind of cumulative effect? Is it beneficial or not from the big picture point of view? We can also, with these kind of tools, we can evaluate that if we do some other, let's say, corrective actions, like reducing the temperature, we could, for example, do that one by changing from natural cooling to active cooling, or we can improve the thermal conductivity of the system by attaching a heat sink or something like that, then we can evaluate the possible effect of those changes. Okay, so how this is done? So again, this is something that quite often I have kind of asked in the intermediate exam, just to explain the basic principles, how this is mathematically done, and for this the most simple case. And this is now coming from the military handbook, and this is the idea is that again you have a failure rate for every component, and then you just calculate the system level or device level failure rate based on just summing up the failure rates for each and every single part. So again, emphasizing that the more complex system you have, more components you have in your system, then the failure rate increases. So the reliability decreases. So how then you calculate the failure rate for a single part or components? So now we could kind of consider that here we have now one single electronic component, like let's say ceramic capacitor. How do we calculate failure rate for a ceramic capacitor? Is that we have first this kind of a steady state failure rate, which means that this is what we want to calculate for that ceramic capacitor. So this is what we then used in the calculation of the whole system. So we sum up this. So steady state meaning that now we are in the, again, in the center part of our bathtub curve. So we are not including the wear out. So that's the reason it's steady state. So where this is coming, it's coming from the generic failure rate. So this is basically a value which is generic for all similar type of components. So in the handbooks or lookup tables, you can get a failure rate for ceramic capacitor. Whatever, it does not matter who has manufactured it or from which materials it has manufactured, but if it's a ceramic capacitor, then it has a generic failure rate. And then you multiply that generic failure rate with these terms T, which can be either smaller than 1 or larger than 1. So meaning that there could be a quality factor. If you purchase a very high quality ceramic capacitor, then this should be smaller than 1. So it decreases the steady state failure rate. Or if you, let's say, select a component which is a low cost one, but the quality is lower, then this could be larger than 1, and then it increases the generic failure rate. Then you have a stress factor. This means that under your system, which kind of stresses except temperature it will see. So for example, now, let's say ceramic capacitor, it is related to the electrical design, voltages, currents, what are used in that system. So is it close to the let's say specifications of that capacitor, or are you far from, so are you kind of playing safe? Then again, this could be either higher or lower than 1, so increasing or decreasing the generic failure rate. And then you have one additional effect, which is coming from the temperature. So again, if you are able to use this component in a temperature which is clearly below the specified maximum temperature, then again, you might be able to decrease the failure rate. So this is also called stress derating. So meaning that with this temperature factor, you could kind of see that, okay, what is the actual effect from the system reliability if I am able to decrease the operating temperature with, let's say, 5 degrees on average or 10 degrees by doing some tricks like, as I already said, putting active cooling or something like that. So getting some estimation on the possible effect of some reliability improvements or corrective actions. So now with these, depending on the system, you can have additional factors. Again, you can have this kind of a first-year multiplier, which means that you have just started to use this component, so you have not yet obtained the experience. So this could then indicate that there are some hidden things which you don't know yet. So that means that your actual failure rate could be larger. So again, could be larger than 1, this factor which you use to multiply the generic failure rate. Or then you have this kind of an experience factor, which means that you already start getting field data showing that, okay, this component is more reliable or less reliable than what you expected. And you can add this one and kind of refine your calculations based on the experience. And so this is the kind of the simplest way of doing it. And then there are other methods which kind of have additional parts. But for now, it is it is enough to understand that what is the basic idea, how do we calculate this failure rate for one component, and then how do we merge together the model for the whole product or unit. So then you just sum up these values, and then you have one additional factor there, which is called environmental factor. So again, this PE could be something which is more than 1 or less than 1, and it means that how the use environment affects on this failure rate in the system. So the use environment of the product or system, how it affects on the reliability of the system. So how do you then get this? Because there's lots of failure rates and lots of factors, so you need, of course, some tools to evaluate those. So you can have these different type of lookup tables, or you can have some tools to calculate those depending on for example, which component type you have and so on. So for example, this military handbook provides quite nice things, nice ways of doing these calculations. And now this method, which I showed you the previous slide, that is called parts count method. That's the simplest method to calculate. So basically, it just takes into consideration the elements and only the electrical elements of the system. So for example, this parts count method does not include the mechanical elements of the system. And then you have other types of methods, like here it calls, in military handbook, it is called detailed stress method, which then uses additional information in order to kind of refine again, get your estimation more accurate with respect to the actual product. But the point here is just that as an example, this is from this Dana Crow's book, one of the cost books, this example, and this is just an example of your alarm watch, how you could calculate the failure rate of the alarm watch or electric clock. So what you have there is different components or parts. So you have the electrical elements, you have the mechanical elements, you don't have any software, and you have basically, okay, operational error. So if you miss the lecture, the problem, of course, could be that you forgot to lift up the alarm button so that it's not alarming you at all. Okay, but what is included in the parts count method is here is that we only include the electrical elements and we exclude all the problems, let's say, that, for example, if the gear or knobs of the clock is failing, that's not included in the analysis. Here we have the how many 8 components. So we have the electric motor, we have the buzzer, we have a switch, buzzer on off, we have the connector to the AC power, we have solder joints, crimp joints, and we have the electrical cord. And here is first the quantity. So how many of those? All the rest we have only 1, but we have 6 solder joints and 2 crimp joints. And then we have a generic failure rate from the military handbook lookup table. We get the generic failure rate for all these components. What is the generic failure rate? And then we have the quality factor for each component. So here we see that, for example, the buzzer switch, on-off switch, that's the quality is rather poor. So we need to multiply the generic failure rate with 20. And then, for example, the solder joints, the quality is little bit worse than on average. So we need to multiply this one with 2, and so on. Then we multiply the quantity times generic failure rate times quality factor, and we end up the failure rate for each component in this system now, and then we just sum up those, and then we end up with the total failure rate. So how many failures per million operational hours? And that is the kind of result from the calculation. And now this was only for one specific method, so parts count method from military handbook. And here is listed some other. So in the telecommunication industry, there is this telecordia or Bellcore way method, which is most commonly used. And it has 3 different methods. And the first method is basically identical to the parts count method in military handbook. And now here in this table, the same method is used to calculate the failure rate. So what you have is basically the same components, same assumptions. You have slightly different failure rates, different quality factors now, because it's defined by the method itself, and then you get the failure rate and you end up slightly different number. So here, this failure, it's given in fits. It's 1 fit is 1 failure per billion operational hours. So there, as I said, there are lots of different standards available in different fields, and then there are softwares which contain these standards or these methods. So for example, Relax is one software package which is quite widely used, and it contains, for example, both this military handbook model as well as this telecordia model. So this is just the comparison. So basically, you have the same product. You should end up with the same number, but using slightly different method, which basically the assumptions are same. Anyway, you end up slightly different values. So according to the military handbook, parts count method, you end up in 66.6 years as a MTBF, and if you use Bellcore method 1, you end up in 75 years as a MTBF. So this just shows that depending on the method you use, you will end up in a slightly different outcome. Then, what are the advantages and disadvantages with this kind of a method is, of course, that if you have the data available, for example, the software, then you can get the reliability estimate with quite little effort. You just pick the components, and especially if your product is this kind of a series, so it doesn't have any redundancy, then the calculation is relatively fast. You get some kind of an easy input to your system level reliability prediction, so you get the starting point, and as the data is based on large databases, then the data is potentially reliable. So I would kind of emphasize here it's potentially reliable, but it does not, of course, always need to be reliable, because databases only have the data on certain amount of data. It does not have all the possible components, solutions which is available in the world. There are standards, which means that if you are doing the calculation and then if somebody else is doing the calculation, you should end up in the same outcome, which sounds kind of naive, but that's not always the complete truth, because there's always some assumptions, and depending on those, you might end up getting also different values. But that's the reason why standards are used, so that you would be able to compare the results. Then concerning the cons, one of course is that always when you're doing these kind of models, the actual outcome result cannot be better than your data. So if your data is out of date, it's not reliable, then of course your results are also out of date or wrong. So and again, what do we calculate here? We calculate these random failures. So again, want to emphasize that this is not something that you can get any data on the actual lifetime of the product. So what you are getting the mean time between failures or mean time to failure values, which tells you what is the probability of the failure during normal operational life. Okay, so this is just some very old data which I have here. So just showing that if you have certain types of failures, what is included and what is not included in these kind of analyses is that, for example, here there's different printed circuit cards from 3 different manufacturers, A, B, and C, and which are the field failures originating from. And you can see here that these are the component failures. So basically now the previous analysis is based on assuming that the components are failing. So basically you include only these. You don't, at least not directly, include the effect of manufacturing or processes. You exclude the software related things and these things. So basically you are missing more than 50% of the actual real causes of the problems in the field. You can indirectly utilize, for example, the manufacturing related things so that you would put these into the quality factors. So for example, the soldering, solder joints, you have the generic failure rate, and then you think that the soldering quality manufacturing is worse, then these failures could be integrated into that component having the solder interconnections and this kind of indirect things. But directly, you only include these component failures in that kind of an approach. So what that really means, that depending on which method, which assumptions you use, then you might end up in this kind of an outcome. What does design update mean? It means that design update is a thing that during the mass manufacturing you notice something. So for example, you notice that there's certain component which starts to cause more failures than you expected. Then you change the design, the component, whatever. So you make some corrective actions during the mass manufacturing, and then you end up kind of decreasing the failure probability, and then you can basically redo the calculation by taking the effect of that change, and then you can get the kind of estimation that, okay, if you can also use that one as a kind of a decision-making tool. So you start seeing that, okay, this is the part or component or whatever which causes us problems, then what should I do? And then you can think, okay, should I change the component? Should I change the attachment method? Or should I change the board layout? Which would be the having the highest effect on the reliability? And then you can also have the cost effects. So changing to other components that cost something, changing to new layout, that the cost might be much higher because you need to redesign the board and everything and these things. So you can also have the comparison between different corrective actions based on that. Hopefully I answered the question. So this is just to show that basically when you are thinking about this kind of reliability statistical mathematical tools, it's completely up to you what kind of result you get. So just playing with the numbers, you can end up whatever value. So of course you need to be consistent. You in order to, for example, you to compare your own calculations. So this is important. And maybe I need to say that this is also something that you can utilize if you are clever enough and you have a customer who wants to compare different suppliers. Then of course you want to have your numbers, the mean time between failures, as high as possible to show that, okay, our product is more reliable, more robust than the other supplier. And then you need to, let's say, try to use the method so that you get a number which is high enough. And that's not always, of course, directly related to the actual real life, but that's how business works. Okay, then now we have on one hand discussed these kind of approach which we use to predict reliability based on the, let's say, component level failure rates. And then let's say the other extreme is that we start analyzing the reliability based on failure mechanisms. So we go there in the actual failure mechanisms, and then we can see that, okay, how you can affect or analyze the reliability based on the actual mechanisms. So both of these have pros and cons, and this physics of failure approach, it's very effective at component level. So if you want to, for example, see that how this one single component is affecting on the reliability, and then you could basically think that how you can improve the reliability. So what you should change in order to get the component more reliable. This is something that is, let's say, MTBF calculations, they just tell you that, okay, this is the actual outcome, but they don't tell you that, okay, what to do, what to change, I mean, in the physical structure or physical design of the component. So that's the clear advantage of this kind of physics of failure. But of course, the problem is that the more complex the system becomes, then more difficult it is to start from the actual failure mechanisms. And these failure mechanisms, physics of failure, they quite often are very effective on wear-out phenomena, but not with the random failures or overstress failures. So again, we are talking about slightly different things. If it's the random failures or is it the wear-out phase. So that means that you need to understand what approach you use in order to verify or improve the reliability at a certain stage of the lifetime. Okay, so we still have a few more minutes to go. So I would like to very quickly show you the other types of approaches. So there are, for example, this fault tree analysis, FTAs, which basically is again this kind of a top-down approach. So you start from the system, and then you start thinking that, okay, what could cause this problem? And these fault trees, they are typically using this kind of standardized symbols to describe these events or logical connections. So basically, this is kind of a programming. So you have the AND gates and OR gates, or basic events and combination events and so on. Maybe best to have an example. So this is an example from, if I remember correctly, it was from O'Connor's book, and it was kind of from shuttle, this kind of a space shuttle or something like that. And the problem was that engine will not start, and then you have an OR. So it is either a problem in the fuel, it is either a problem in the carburetor, or is it an ignition problem. And then we have again another OR operators. So why fuel flow could be failed? It could be a fuel pump failure, or it could be a clogged filter. If it's an ignition failure, then they have a redundant system. So they have ignition system 1 and ignition system 2. So in order this to be the reason, then you need to have this ignition system 1 and ignition system out of order. So this is just a way to start thinking about going from system level down towards the component level, to think that, okay, what could be behind a certain failure. And now it's quite easy to understand that if you would have a very complex system like space shuttle, then you cannot go very deep down, because then this picture would become extremely complex and impossible to use manual way of drawing it out. You have softwares. What is the difference between circles and rectangulars eye-looking symbols? So basically here the basic description was here in the here. So it means that for example, this system means that there is something also lower, but this is basically then transferred to a lower level fault tree. So in this fault tree, it is not continued downwards, but you can have another one, which is kind of describing what is inside here. So this is something that if you're more interested, please go to the O'Connor's book, and you can see all these different symbols and markings, what is actually behind there. Okay, so this is another, let's say, similar type of analysis. So it's called reliability block diagram, RBD. So here we have the same problem. And now here we have the fuel system, here we have the carburetor, and here we have the ignition system. And now we can see that these are in series. So it is or this failure, or this failure, or this failure. And then we have the ignition system, which is redundant. Here we have this and this. So both needs to be failing in order to this to be causing the problem. So this is just a way to, let's say, visualize the brainstorming for trying to understand, figure out the problem from system level downwards, as deep as you want to have. So basically the mathematics or way of thinking is the same for both of these fault tree analysis and reliability block diagrams. But as I said, please, if you are interested, check this, for example, O'Connor's book, or just Google them. There's huge amount of nice information on that. Okay, so we have few more minutes time. So like to start few words on automotive electronics, and then we can continue on Thursday from this. So I think these are quite obvious for all of you. So I'm kind of going through this quite fast. So we all know that we have two mega trends in automotive electronics. We have the electrification. So electrical cars, hybrid cars, and then we have the autonomous driving. And both of these kind of have an effect of the components and parts needed, and also if we want to analyze the reliability, then of course we also need to think it from different application viewpoints. So one maybe critical thing which is not that obvious is that the electronics, the cost of electronics in cars is increasing drastically when we go towards the autonomous driving. So now we are somewhere here. It means that roughly 1/3 of the total cost is already coming from the electronics in the cars. And then, of course, as many of these things are related to safety, it puts lots of emphasis on the electronics reliability. And that's kind of course, challenging, but also nice for us because there's lots of things to do. So we have different types of electronics, naturally, and it is nowadays quite heavily based on sensors. So you need to measure something, and then based on the measurement, you need to do the actuation. Of course, already during the old combustion engine cars, you had these lambda sensors measuring the exhaust gases and adjusting the fuel air ratio and so on in order to get decrease the amount of let's say unburned gasoline in the exhaust gases and so on in order to be more effective in utilizing the energy. But nowadays, of course, there's lots of other things, not only the engine management, but also in the safety related issues and also in the comfort kind of thing. So you want to have different type of things like particle filters and GPS connections and everything, parking assistance in your car. So that is, these sensors are nowadays becoming more and more critical, and there are especially MEMS sensors are coming. Why? Because of the size, because of the cost, because of the power consumption. So MEMS in general have very nice advantages in comparison to let's say traditional sensors. So you might, for example, think about the gyroscope, traditional gyroscope, which I'm not sure how many of you have seen those in the army, but basically the gyroscope could be something like 1.5 meter wide ball, which is rotating and measuring the rotational accelerations in order to really in detail define your position. And now the same functionality could be done in few millimeters times few millimeters component. So that is the basic thing. Okay, but I think that the time is up, so I will continue a few more slides on automotive electronics on Thursday, and then we discuss also a little bit more in detail about the environmental stresses. So, let's see.